We hear all the time that machines can learn from data, but how? How do they actually do it? What are the recipes they're following to make these incredibly smart predictions? Well, in this explainer, we're going to take a simple tour of the core machine learning algorithms that are powering the AI systems all around us. Let's dive in.
All right, so here's our game plan. We'll start by figuring out the difference between a recipe and a dish in the world of AI. Then, we'll get into how machines predict things when they already have the answers. We'll check out the power of decision trees, see how AI can find patterns all on its own, and then we'll put our whole AI toolbox together.
Okay, first things first. We need to get one really important idea straight, the difference between an algorithm and a model. Seriously, once you grasp this, everything else in machine learning starts to make a whole lot more sense.
Think of it like this. The algorithm is the recipe. It's the set of instructions, the step-by-step guide for how to learn from data. The model, on the other hand, is the finished dish. It's the thing you get after the algorithm has done all its work, after it's been trained. It's the expert system that can actually make the predictions on new stuff it's never seen before. So here's how that process actually looks in practice. You start with a big pile of raw data. Then you pick your algorithm, your recipe. That algorithm then crunches through the data in a process we just call training. And what pops out at the very end? The final trained model, all ready to be put to work.
And you know what? This cooking analogy is just perfect. The algorithm is the detailed method you'd find in a cookbook. The model is the delicious, finished meal that you actually serve. One is the process, the other is the final outcome. Okay, now that we've got that down, let's open up our toolbox and look at the first two major tools. These are for something called supervised learning, which is just a fancy way of saying we're working with data that already has the correct answers labeled for us. So let's start with a classic real-world question. Imagine you've got a ton of data on houses. You know their size, their location, how many bedrooms they have, and now you want to predict the price of a new house. You're trying to land on a specific number.
For any kind of how much or how many question, you're going to reach for a regression algorithm. These guys are built to predict continuous numbers. They basically figure out the complex mathematical relationship between all a house's features and its final price. This is the engine behind everything from Zillow's home estimates to Wall Street's stock predictions.
But what about a totally different kind of problem? Here, we're not predicting a number at all. We're just trying to sort something into a category. Is this email junk or is it important? Spam or not spam?
And that is the job of classification algorithms. The key thing to remember is this. Regression predicts a number along a sliding scale, but classification just sorts things into separate buckets. These algorithms learn how to draw a decision boundary, like a line in the sand, that best separates one group from another based on all the examples they've seen.
All right, next up on our tour is a really powerful and, honestly, pretty intuitive type of algorithm. This one learns by creating a set of simple, human-readable if-then rules. A decision tree works by figuring out the best questions to ask to split the data. And here's what makes them so cool. They're transparent. You can literally look at the flowchart it creates and understand the logic the machine came up with. This is absolutely critical in fields like finance, where you might have to explain exactly why a loan application was rejected.
So that gets you thinking, right? If one decision tree is pretty good, what happens if you combine the wisdom of a whole bunch of them?
This is where we get into something called ensemble methods, basically teamwork for AI. One method, called a random forest, just builds hundreds of different trees and then takes a majority vote on the answer. It's like asking a huge crowd for their opinion. Then there's gradient boosting, which is a little more clever. It builds trees one after the other, and each new tree's main job is to fix the mistakes that the previous tree made. It's this teamwork that makes these some of the best performing algorithms out there.
Okay, now, everything we've talked about so far assumes we have data with the right answers already labeled. But what if you don't? What if you just have a massive pile of data and you want the machine to find interesting hidden structures all by itself? Well, that's where unsupervised learning comes into play.
The most common kind of unsupervised learning is called clustering. A clustering algorithm just looks at all your data points and finds natural groups, or clusters, where the items inside a group are way more similar to each other than they are to items in other groups. Businesses use this all the time to find different segments of customers, but it's also used for things like grouping similar news stories together.
This simple quote is pretty much the entire philosophy behind another really fascinating algorithm. It works on the simple but incredibly powerful idea of similarity.
Now, the key thing about k-nearest neighbors, or KNN, is that it's kind of lazy. It doesn't build some big, complex model beforehand. Instead, when a new, unknown piece of data shows up, it just looks around at its k closest neighbors in the existing data. So if k is 5, it finds the 5 data points that are most similar to it. If, say, 3 of those 5 neighbors are in the blue category, it classifies the new point as blue. It's that simple. You are what your neighbors are.
Okay, so we've looked at regression for predicting numbers, classification for sorting into categories, decision trees for learning rules, and clustering for finding hidden groups. This brings us to a really important high-level question.
I mean, why isn't there just one master algorithm that's the best at everything? Why do data scientists need this entire toolbox filled with different approaches?
The answer really comes down to a simple idea. There's no such thing as a free lunch. Different problems need different tools. A decision tree is super simple and easy to explain to your boss. A gradient boosting model might be more accurate, but good luck trying to explain how it works. The type of problem you have, the shape of your data, and what you actually need to accomplish, that's what tells you which tool to reach for.
And of course, you're probably wondering, hey, where do the famous neural networks and deep learning fit into all this? Well, there's simply another incredibly powerful family of algorithms in this very same toolbox. They just happen to be especially good at finding super complex patterns in things like images and text. And that's a story we are very excited to explore.
So that wraps up our quick tour of the classic machine learning toolbox. Before we go, we just want to take a quick moment to share our mission with you.
But first, and most importantly, thank you so much for taking the time to learn with us today. We really appreciate it.
Our channel is called Knowledge Equity Partners, and we're a multilingual space where our whole goal is to share contemporary and practical knowledge on all sorts of topics that can help make your daily life more effective and efficient.
So if you found this content valuable, we'd love it if you'd subscribe to Knowledge Equity Partners. That way, you'll get notified about our new videos. And of course, don't forget to like, share, and spread this practical knowledge with your family, friends, and your community.
Let's work together to keep the quest for knowledge always high. And speaking of which, we'll be back soon to continue the story of neural networks, starting right at the very beginning, with one of the first algorithms ever inspired directly by the human brain. We can't wait to see you then.